Welcome back to our continuing discussion of options. We turn now to a group of ideas that are collectively known as the option Greeks. To begin, we have to consider various different ways that risk has been measured with respect to option contracts. One of the popular methods that we will look at soon is VAR, or VAR, value at risk. We'll also consider some such as the interest rate sensitivity measures of gap and dollar value of a basis point and convexity. For today, our focus will be on the derivative-based sensitivity measures delta, gamma, vega, rho, theta, and related ideas. Delta is one of the Greeks that receives considerable attention. It measures the sensitivity of the put or call's option premium to the underlying security's market price. We see the change in the asset value due to changes in the underlying in the delta. We measure delta as delta V, change in value of the option contract, divided by delta P, the change in the underlying security's market price. From the calculus, you will remember that as we approach a limit wherein the change in the underlying security's market price approaches zero, we translated delta V over delta P into dV dP. And furthermore, when we moved from having a simple relationship between a dependent and an independent variable to the situation where we have multiple variables and we held all constant except one of interest, then we used a so-called partial derivative. So we say the first partial derivative of the value of the option with respect to the underlying security's price is the term that gives us the delta value that we will use. Let's turn now to our application of delta. Let S be the underlying security price and consider what happens when it increases. Then C, the call premium associated with that, would similarly increase. And conversely, P, the put premium of a put associated with that underlying security, would decrease. This effect is known as the delta. We measure delta from N of D1. Recall, we defined D1 in our earlier lecture and noted that N of D1 was the cumulative normal distribution from negative infinity to the deviation D1. Delta approximates the call premium change over the underlying security's price change for a very small stock price change. We often seek delta hedging or delta neutrality, that is, a situation wherein the delta for a portfolio does not change as the components of the underlying portfolio change. If we take the product of delta times the number of calls that we have in a portfolio, the result tells us the number of shares of the underlying security that we need to own in order to reach delta neutrality. That is, as one goes up, the other one goes down by a commensurate amount that offsets this. We achieve effectively a risk-free hedge over the next instant in time with delta hedging. Gamma The next of Greeks that is of interest to us here measures the delta's sensitivity to the underlying price. That is, how does delta change as the underlying price changes? It turns out that there is a change in delta that is due to changes in the underlying securities price. You should recognize this as the derivative of the derivative. We call that the second derivative. Gamma then is measured as delta delta over delta P. That is the change in delta over the change in the underlying securities price. And in turn, we often represent this as the first partial derivative of delta with respect to P, the underlying securities market price. Gamma then measures the change in delta over the change in the stock price. The big thing here is that it picks up the effect of larger changes in stock price. We measure gamma as e raised to the minus d sub 1 squared power divided by 2, that entire quantity over the underlying security price times its standard deviation times the square root of 2 pi times t, the time remaining until the option contract expires. Our next so-called Greek, vega, despite the fact that vega is not really a Greek symbol, is a measure of the change in value of an asset that is due to changes in the volatility of the underlying financial price. Vega then is defined as delta V, change in value of our derivative, with respect to delta sigma sub P, the standard deviation of the price of the underlying security. We simplify this to the first partial derivative of V with respect to the standard deviation of the underlying securities price. We can calculate vega from the equation S times the square root of t over e raised to the d1 squared power over 2, all divided by the square root of 2 pi. The variance, or standard deviation, is the most sensitive variable in the Black-Scholes model. The option premium changes considerably with respect to volatility. Furthermore, this is the only unobservable variable. When the underlying securities volatility, or standard deviation, increases, we know that the call premium is expected to similarly increase. This effect, again, is known as vega. We could also consider the exercise price, and as we would expect, when the exercise price increases, the call premium is expected to decrease. This is a somewhat less interesting relationship simply because it's nearly a more trivial relationship. We can also look at the risk-free rate and how changes in it affect valuation. If we take the natural logarithm of 1 plus the discrete risk-free rate, we get the continuous risk-free interest rate. As the risk-free interest rate on a continuous basis increases, we expect the call premium to similarly increase. This effect is commonly called rho. And rho is calculated from the equation T, the time remaining until the option expires, times the exercise price of the option contract divided by little e raised to the RT power, all times the quantity N times, or N of D2. The time to expiration can be calculated in several different ways. A simple approach is to simply take the number of days until expiration divided by the number of days in a year. As the time to expiration T increases, we expect the call premium to similarly increase. This effect is referred to as theta. Let's turn now to theta. This is the premium decay over time, how much the premium declines per unit of time passage. This is the first partial derivative of the premium with respect to time. That's the first partial of C with respect to T. We calculate theta from K times little e raised to the minus RT, all times the quantity standard deviation times the first derivative, the derivative of the first derivative of N of D2, all divided by 2 times the square root of T, and we add to that risk-free rate times N of D2. These risk measures have certain limitations that we have to keep in mind. It turns out we cannot aggregate the different types of risk that we are measuring here. That is, the elements are not additive. The capital that is at risk is not being measured directly. Furthermore, control measures are not readily available for us to understand exactly what's happening as these changes occur. Let's conclude our discussion here, and we'll come back in our next session and extend our look.